wooden big pointer.
Yeah, we should have a stick. They are
Ruler? Where is the
right?
Second floor. We have it on the second floor.
okay?
Yeah, we are still.
It's flipped. Oh, you're viewing yourself, so it's flipped.
Yeah, but
I see. I see.
it's not properly.
It looks fine here. It's just that you need to zoom in there.
Yeah. Glasses, yeah. I couldn't just sleeping. Please don't pay attention. Of course.
You saw there's a 400-page paper on the archive today. Yeah, something like 419 pages.
It's on the thesis.
No, it's a paper. Someone posted it's actually relevant to my research. It's about enumerating Higgs operator basis in n square LO. Right. So they just dumped all the equations, all the, something 10,000 operators there. Yeah. Super long.
Yeah, he's very proud.
Yeah.
How long?
How they can publish it?
I don't know.
The whole issue of the journal. Or...
Yeah, it's a whole journal. Yeah.
Yeah, like experiment.
No, but they still make.
Oh, there's an SDI post. There's no journal. SDI post is an electronic publication.
Oh, that's where it was sent to.
Probably it wasn't there because that is reference, but no, that is all electronic.
Sign post?
Yeah, SDI post.
Yeah.
Yeah, I guess, yeah, only PRD. I mean, because I don't, JHAP doesn't, JCAP, they don't make paper versions either.
Yeah. Others would like to use SCI post because they posted the referee report there as well.
Oh,
Other people can see. Yeah, people can comment on those papers.
Also, everyone can see the referee report.
Yeah, and the referee can choose to be anonymous or not.
Right.
Yeah.
Yeah.
It's considered as a referee application.
Oh, laser. Oh, thank you. Working.
Today we're very happy to have Xiaochuan Lu from University of San Diego. He got his PhD from UC Berkeley under Koichi Murayama, and then he did postdocs at UC Davis, University of Oregon, and now at San Diego. Today he's going to tell us about STEM model, EFT, and PL.
Okay. I'm very happy to be here, and thank you for having me here. And this is actually my first in-person seminar since the pandemic, and I'd say it feels really good to have this in-person interaction. Thank you very much. And today I'm talking about about general effective field theories, but I'm going to take the standard model effective field theory as an example, basically to explain a few basic important aspects in general EFT techniques. Okay, so let me get started. I need to use this, but okay. So first, we know about a decade ago, we found a Higgs boson at the LHC, and it's around 125 GeV. So now we know so far this Higgs boson is very consistent with the standard model of particle physics. So if you look at the standard model now, every particle is discovered there, and it's a pretty good story for the nature we understood so far. However, we know that there are still many questions not answered by the standard model itself. Just to name a few, we have on the experimental side, we have such as dark matter, neutrino mass, baryogenesis, and so on. And there are also theoretical concerns such as hierarchy problems, strong CP, and cosmological constant, and a lot more. So certainly we know there are motivations and also observations for physics beyond standard model. So we know there are physics beyond the standard model. So the next phase for particle physics is like, how do we probe those BSM physics? Then of course, one approach is you consider a variety of UV models, such as supersymmetry, composite Higgs, neutral naturalness, extra dimension, and of course, many more of those. But you can also have an alternative parameterization of the UV physics, and that's the subject of my talk today. That's the so-called standard model effective field theory, where you think about all those physics beyond standard model just as additional interactions beyond the standard model Lagrangian, and then you supplement the Lagrangian by this non-renormalizable interactions or higher dimensional operators. Then that's the framework of standard model effective field theory. So in fact, this is a natural way of thinking about it because EFT in general is a general approach in physics when you think about, you have a separation of scales, right? So the first example of EFT is arguably this Fermi's theory of weak interaction, right? This for bit decay. So we now know there are W and Z bosons in the standard model, but back to those days, you can just, because the energy of the experiment is so low, you can just shrink it and you zoom out and you find this full fermion interaction as an effective theory. So that's an example, the prototype of EFT. So nowadays we have many examples of that after this Fermi's theory. So we have like QCD Carroll-Lagrangian, a heavy quark effective theory, soft collinear effective theory, and low energy effective field theory, and also this example I will talk about, which is a standard model EFT or Higgs EFT, sometimes people call it. And I will tell you about the difference later in this talk. So that's about this Lagrangian. So this is a natural way of thinking because especially if the new physics is at a relatively high scale compared to the electroweak scale. So if you have a scale separation, so using an EFT to parameterize the new physics is the natural way. Okay, so here is an outline of my talk today. So I will take the standard model EFT as an example and explain several conceptual and important aspects of EFTs in general. And basically they cover this, like how to define EFTs in general. So that is in case of SMEFT is basically what is SMEFT. So here I will emphasize how to construct EFT operator basis. Then second, about generally applying EFTs, that is how to use this SMEFT. Then it has basically two main aspects. One is how do you use that as a theory itself to interpret experimental observations? And second is once you have the EFT, then how do you make use of that to as a hint for more fundamental theories, more UV theories? Okay, then third part of my talk is I will discuss some deep challenges for EFTs in general. And then in case of SMEFT, that is right, the question of is SMEFT enough? And here I will tell you that it's not enough. And something called heft is needed when you have non-decoupling BSM physics. And then I will explain to you some geometric picture to address field redefinitions in EFTs. And here, the traditional picture doesn't account for field redefinitions with derivatives. So then I will also tell you the most recent progress is how to accommodate also field redefinitions with derivatives. Okay, so as you see, I will cover several different aspects of effective field theories. So in this talk, what I will try is to give you the main ideas and basic the motivations for all these aspects, because the details could easily get lengthy and very boring. So I will try to eliminate the equations as much as possible in this talk. But if people are interested in any specific topic here, then I'm happy to answer any questions and discuss in depth afterward. So that's what I will explain in this talk. Okay, so let me get started with the first part of defining EFTs. Okay, so how do you define an EFT in general? Or in case of SMEFT, it's this. So you specify the particle content and the symmetries. So in terms of standard model, it's like you have all these particles, and for each particle you assign this field, and you have this standard model gauge symmetries, and you write down all the allowed interactions respecting the symmetries with this fields, then that's your Lagrangian. And if you truncate, you require your theory is a renormalizable one that is in 4 space-time dimension, that is with a mass dimension smaller or equal to 4, then you get the standard model Lagrangian, and that's the standard model. But if you also allow for non-renormalizable interactions like here, then you basically get SMEFT. So that is how you construct an effective field theory in general. You just allow yourself to turn on non-renormalizable interactions. And that's okay because by definition of EFT, you will truncate this series. So you only have a finite number of counter terms to deal with. So that's a well-defined predictable theory. That's EFT. So for the case of standard model or SMEFT, at dimension 5, you have this famous Weinberg operator. That's the neutrino mass operator with L square and H square. Then at dimension 6, it looks like this. So this is a famous Warsaw basis operators. So you have bosonic ones and fermionic ones and 4 fermion ones here. So that's dimension 6. Okay. So in this construction of general EFTs, you need to deal with this redundancy problem. So you think, okay, I just truncate this dimension 6, I just enumerate all the allowed operators, right? But the tricky part is there's redundancy. For example, in the SMEFT dimension 6 case, for this 4 fermion operator, a lepton, 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 you could either have a sigma A inserted here and contracted. That's a polymatrices for the SU2, or you just don't have them. So they look like two different operators at this level, but actually they're the same due to this group identity for SU2. So this TA is the SU2 generator, and then so you see they're the same. So this is an example of operator redundancy, right? So if you just naively write down operators, there are secretly some relations among them. Okay, so in general, for EFT operator basis, you encounter this three types of redundancies. Group identities such as this one, right? And also secretly using Fields identity here to really link those two operators in. And also another is inversion by part. And another one is equation of motion. So there are three types of redundancies. So what you want to find is a set of effective operators that will not be linked by those redundancies. So it's a minimal complete set of operators. That's the concept of an operator basis. Okay, so it turns out that finding the set of operator basis is a non-trivial task. So for example, you can see this history of SMEFT operator basis. So at dimension 6, the first attempt was in 1986. And it turns out that they overcounted some operators. Then later on in 2010, the Warsaw basis came out, but they still overcounted some baryon violating operators for one generation. So they have 5 there. Then later on in 2013, Alonso, Jenkins, Manor, and Chod pointed out that it's actually only 4 if you have just one generation of fermions. So this is the first time we have the fully correct result for dimension 6 SMEFT. Then you go to dimension 7 and 8, then you find that people mess up again at dimension 8. So then the correct result was later on obtained that year later. So you see clearly, this is a non-trivial task. There
Excuse me, what is N sub G?
Oh, N sub G is the number of the generation of fermions.
Don't we know that it's 3?
It is 3, yes.
So what's the point of calculating something for one generation?
Oh, yeah, that's a good question. Yeah, for practical relevance, you want to set NG equals 3.
Okay.
Yes, yes. But sometimes people talk about, flavor universality, like you want to minimize the flavor violation. Then, yeah.
So, Misha, for 3 generations, there are many more operators if you allow flavor non-diagonal terms. So they are counting so-called flavor universal series, only diagonal couplings are there. If you include the off-diagonal ones, I believe dimension 6 is like 2400 operators.
So what can you
2,499.
if you take their way, or the path into just counting without any outside idea, any operator of dimension 6, and we know that in our nature there are 3 generations. What's the point of considering? If you have some idea additional, why not? You have to count all each and every operator, right?
Yeah. So yeah.
Then, but okay.
Yeah. So people counted that's 2499 operators at dimension 6 level.
Yes.
And many of them are flavor violating, well constrained by our precision.
Well, you can discard among this. Anyway, there will be extra because if it's, let's say, 4 fermion operator, you can take 2 fermions from one generation, 2 fermions from the second generation, and it's not flavor violating, right? But it's not counted in this type of count.
Yeah, that's completely right. Yeah, I completely agree with you. Yes.
Yeah, that's another 3 generation diagonal.
Yeah. You can take NG equals 1 as an exercise such that you can calibrate your technique and make sure you're not making a mistake, right? So you get 1 generation right first before you go to 3 generation to get some confidence.
I guess the intermediate step would be when you say I have a minimal flavor violation. Whatever that diagonalizes the mass space is also diagonalized. So you cover, but then right, of course, 1, 1, 2, 2. Right.
No, dimension in if you build all dimension 6 operators, it's not as easy as just generalize diagonalize the mass matrix, because the mass matrix has a very specific form. When you are up to dimension 6 operators, you have much more freedom.
Yeah. That-
And for instance, mass term is
That's true.
right and left, and here you can have
Yeah.
The gamma of mu,
Yeah.
for instance,
Mhm.
gamma 2, gamma psi bar, gamma mu psi square.
Mm.
It won't be diagonalized with the diagonalization of the
Yeah.
mass matrix.
Yeah,
It's a different.
people write certain ansatz, right? So it's
Mm.
what they call minimal flavor violation.
Mm.
Right?
Mm.
There is certain rule,
Yeah.
in certain sense can be diagonalizable.
Mm.
In other words, you just throw away the operators. You don't like.
In practice, it's just so many operators to deal with for 3 generations. So sometimes people just simplify it. There's a
Yeah,
question.
so I have a way more naive question just to make sure I'm following. So
Sure.
if you undercount the number of operators,
Mm.
that's very bad because it means you probably missed some important
Yeah,
physical.
that's right.
If you overcount, then really you may think that there are more in low energy constants than there really are. And if you then go on and do calculations, you'll discover that
Right.
mysterious reasons some low energy constants will be equal to each other.
Right.
And it's nice to know how many to expect a priori. So that's what getting the count right
Mhm.
is good for. But I guess if you have an algorithmic procedure for generating all of these operators, you can be confident you don't undercount. And that's more, in a sense, more important because undercounting is a disaster. You want to make sure you don't undercount. Is that right? Or what's the hard?
You're right in that sense, yes. But then when it comes to like when you want to link a certain UV theory with your EFT,
Yes.
right? Say you have a UV proposal and you want to match it with the EFT. Then if you overcount, you saw there are too many degrees of freedom to determine, but they are secretly linked. Then you will find solutions where you find equations to determine all those free coefficient in front of those operators. Then you find, okay, I cannot find enough amplitude to determine that. So it could be bad too in that sense.
I see what you're saying.
Right. So overcounting is also right. You have an overcomplete basis. They're not really a basis, but when you want to determine all those variables, right? It appears that. Right. Yeah.
Yeah, you should get the count right.
Right. Right. Yes. Okay. Mhm.
For your paper with Hiroshi,
Mhm.
you did correct counting for.
We believe so. Okay.
But can you modify your formula to count the ng equals 3 result to get all the flavor of diagonal lines as well?
Yeah. It is there. Yeah, of course. Yeah. So this is just giving you an example of ng equals 1. Yeah. Okay. So let me move on. So then the way we counted operators, right, or enumerate operator basis is that we use this systematic way of doing that. It's called the Hilbert series technique. It's quite technical, but then the basic spirit is simple. It's just that you enumerate all the field content there, and then you consider all for each field you have all those components. Then a generic operator is just some power of all those components you consider. So this is the space of all the possible operators, right? Then you just want to select out from this whole giant set that the gauge singlets, Lorentz scalars, and conformal primaries such that it's not a total derivative, right? And then this is your operator basis. So the basic spirit is very simple. How to exactly achieve this selection is technical, but the spirit is just this. Okay, that's the method of Hilbert series. Go ahead.
Why do you want to restrict to conformal primaries?
Oh, because this is the integration by part redundancy. So if you have an operator that's a total derivative, so usually apart from topological terms, we would not think it's a meaningful operator in the Lagrangian. Then if you organize operators in terms of conformal representations, only the primary one, the top one, is not a total derivative. All the descendants are total derivatives.
I understand.
Yeah. Okay. Thanks. Okay. So this is the technique we use to enumerate the operators. So then here is coming back to your question. This is a number of SMEFT operators for one generation here, like dimension 8. This 993 is here. 3 flavors, 3 generations is just here. You have some 44,000 operators, and you can go to higher dimension and then get the right. So if you enumerate, if you list out all the operators, then you can see what happens. It's super long, right? So
sorry, for dimension 6, why do you count 24?
Yeah, that's the number of the real coefficients. So 59 is the number of operators because people did it manually, right? But then some of them are Hermitian conjugate, and then yeah, they're complex operators. So yeah, okay. So then this is just the number. If you look at what Hilbert series actually give you, for example, this dimension 8 and 993, it looks like this. So it does give you the detailed structures of this operator basis. You know, like what they are roughly. Yeah, so that's what the Hilbert series gives you. You see all the 993 for one generation is here. And you can do the same for 3 generations.
This is roughly because the coefficient, the number in front of each term tells you how many independent operators that form are.
Right, you still need to figure out such as the detailed Lorentz contraction structures and group indices contraction structures, right? So this, for example, if you can see this is 2 here or something 4 there, so you need to still do that. So Hilbert series doesn't give you all the way to the operators yet, in this sense. But it's not hard. If you know this category only has like 3 operators, then you do it by hand from there, right?
But there's a chance I write down the operator is actually a linear combination of the other operators. So,
yes.
So in some sense,
yes.
I can. This is insufficient for me to write down.
It's not all the way to, yeah, but it gives you the basic guidance of like you want to cross check with this to make sure you don't mess up, right? So, okay, good. Okay, so nowadays the application of Hilbert series is like a glance of that is like this. So originally it was introduced to count like gauge invariance and flavor invariance, right? But this is before people knew how to handle the redundancies involving derivatives such as equation of motion and integration by part. So then we enabled that, and so now you can use that to count the whole operator basis. We apply this to SMEFT, Carol-Lagrangian, and also HEFT, which is this paper should appear soon. We found that this is successful and agree with the literatures.
What is HEFT?
HEFT is a Higgs EFT. It's a nonlinear realization of the electroweak symmetry breaking. Any other questions? So this is my first part of the talk. So you see, I'm trying to stay sketchy and at the summary level. Go ahead.
So on that plot where you were showing the number of operators,
yes.
Like in general, it's harder to make odd dimension operators than even. Is there some like deep reason behind this? Because like if the standard model had some gauge singlet scalar, then I imagine I could just always take the dimension 6 operator and slap that on, and that would give me the 7.
Yeah, all dimension is
in the standard model.
Yeah, all dimension is simpler in that sense because of fermion. So fermion has the right, it comes in pairs, so that's a side by side is dimension 3. So yeah.
Okay. I guess this seems like a theory dependent statement. I was wondering if there's something about this standard model that makes it harder, but yeah, I guess I can believe that this is true.
Okay.
If you have a singlet scalar, a new theory, I think that then it would be more smooth.
Right.
Yeah.
Right. But you don't have it in standard model because you use capital H instead of little h. Right?
Yeah. Because the all-dimensional singlet is by fermion bilinear. That's the standard model. That's why.
Okay. Done. All right. Let's move on to my second part of applying EFTs. So in this part, we talk about these 2 aspects. One is you interpret the experimental measurement with SMEFT, right? And the other is now if you suppose you find the SMEFT with some non-zero, what we call boson coefficient, the CIs here, then how do you use that to lead us to the more fundamental theories, right? That's the ultimate goal of theoretical physics, I guess. Okay, so let me talk about the first part. So the first part is basically the task of place limits about the boson coefficient. So that is interpreting zeros given the current status of the experiments, right? So if you look at this part, then one thing we would like to notice is that if you just search SMEFT and LHC on Inspire nowadays, then you realize that it's getting growing attention in recent years and the number of papers and citations. Okay, so this is certainly people are really getting serious about using SMEFT at the LHC. Okay, but very unfortunately, even nowadays, it's still highly controversial how to exactly use that at the LHC. So you can see this is the LHC EFT work group note published earlier this year. So they're talking about truncation, validity, and uncertainties. So highlighted here is here. So this is a note basically summarizing the status, and then no consensus was reached and no formal recommendation is therefore put forward at this time. None of the proposals have been approved or validated, and further work is needed to establish a prescription. So that's the status for how to use SMEFT at the LHC today. Okay, so there are political reasons behind this note, of course, but then there's also physics reasons. I will stay away from the political ones, but then tell you what's the physical reason for that? So the physical reason is very simple. So if you look at, for example, global fitting result nowadays, like the most up-to-date thing, then what are the limits of the boson coefficients for SMEFT? So how big are they? So in terms of energy scales, right? We know electroweak scale is something like 125, 200 GeV, 246 GeV, right? Something like that. Okay, then the bound we place on the boson coefficient is typically at a few TeV. So that's the situation, right? Depending on which boson coefficient you're talking about, but typically the bound is at a few TeV. But the LHC is arguably running at a center of mass energy of 14 TeV. It's higher typically than the bound for the boson coefficient. So we know EFT by definition is a low energy approximation. So if your experiment is conducted at an energy much lower than your cutoff scale, then EFT is a good approximation. But we're talking about the SMEFT with UV physics scale a few TeV, but we're running the experiment technically at 14 TeV. So of course it becomes unclear if this EFT is still a good approximation at all. So the physics reason behind this debate is very simple. Okay, so in general, this question, you have an EFT in, any EFT, not just SMEFT. It's by definition a good approximation at low energies. So when you do experimental well below your new physics scale, then it's valid. But if you do your weak decay thing, if you do your weak interaction experiment well above WZ mass, then of course the Fermi theory for fermion theory wouldn't work, right? So you know that it's invalid. But the LHC is like this. The energy zone of the experiment is across this new physics scale at the moment. So it's not that clear. That's the reason, right? Because it's a hadron collider, right? There's a proton PDF. So then it's the distribution of the center of mass energy at the partonic level is a distribution like this. So it's not clear. So that's the reason. So what do we do then, right? So I'm not going to touch the uncertainty yet. I will just explain the validity part. How do you know your EFT is a valid approximation for this kind of experiment? So one approach, of course, is if you know your UV theory, you can just compare your EFT prediction with your UV prediction and check if it's a good approximation, right? All you want is for EFT as a good approximation, right? So if you knew your UV theory, you can just compare and check. But the point, of course, is to use EFT in the first place is that you don't know your UV theory. You want to be, parameterizing the new physics in a model independent way. So if you do that, you need to develop some bottom-up way of suppose I don't know what the UV theory is. I just give you an EFT Lagrangian with the boson coefficient. How do I know this will be a good approximation of certain UV theory, whatever that UV theory is? That sounds like a question impossible to answer, right? So then, but then we think about this, then it's like, okay, you don't know the true answer. You only know the EFT approximation, but you want to tell if that's a good approximation. We actually deal with this problem every day in quantum field theory. This is the famous perturbation theory, right? So the QFT gives you a path integral you calculate. Ideally, you want to do the full evaluation of the result if you could, but you don't know how. So you do perturbation, you truncate, you do approximation, you do tree level calculation, 1 loop and 2 loop as an approximation. Then you want to know, is that a good approximation to the full answer, to the real answer I'm supposed to get? but you don't know the full answer. If you knew, you just directly compare, but you don't know. Then what did you do? You say, okay, let's take this something called partial wave unitarity as a hint. If I do tree level calculation and cross section, I find the unitarity is violated, then that tells me something is going wrong with this approximation. So I get a hint of the validity, right? So that's the way. So we're just proposing the same thing. You can use the partial wave unitarity as a hint for the EFT validity. So if you find the unitarity is violated, then that tells you your approximation is not reliable anymore. Okay, that's the basic idea. Go ahead.
What is an example of an effective field theory where it makes sense to trust it when you use a word lambda? I thought that unless you use much smaller number, you never trust it. So like the only case you trust is the first one, and the other two.
Okay, so imagine a case that your experiment is a mix of energy zone. Most of them is here. Like 99.9999% of events come from this energy zone. One tiny contamination from some cosmic rays from here. Do you trust your Fermi theory for beta decay?
Right. Is order lambda, roughly speaking, after a factor of 2, you can use expansion in 1/lambda. It's like Fermi approximation for the weak interactions. If you go with the Fermi formula for the cross section, for Fermi interaction, they're all linear, right?
Yeah.
If you go up to the W boson mass, of course you do a mistake because, okay, starting after the W boson mass, it all flattens off and becomes logarithmic. But right at the W boson mass, you make a mistake of a factor of, I mean, there is a factor of 2, so it's not order something.
I see. So, okay.
Yeah, thanks.
One
Yeah.
perspective is that you're trying to understand when the order 1 mistake set in.
Yeah, it's because the energy zone is not a pinned, very narrow. It's inclusive enough in that sense. So you have some distribution. So you.
It's also a function that you want to study that the hadronic collides, right?
Right.
If,
Right.
If this would be a plus a minus and you overstep.
Right.
Then okay.
Right. Right.
Here it's only in statistical
Yeah.
sense. Sometimes it's
Exactly. So because you're talking about a hadron collider, right, or any kind of inclusive event set, you don't know the precise energy. You only know it's from somewhere from 0 to 14 TeV. It's a distribution. You don't know the exact number.
Yeah.
Then the question is unclear, right? Is your EFT still valid, right? Then you want a criterion to tell you that when it's valid, then, right, it's a complicated question. Yes. Okay. Okay, so then let's move on to the second part then of this applying EFTs. That's once you find the Wilson coefficient, suppose you get some non-zero thing, or you get a bound for the Wilson coefficient, then you want to eliminate some UV possibilities, some class of UV series that is no longer viable and is there, right? So you basically in this part, you need an efficient way to map between the more fundamental UV series with some beyond the standard model heavy particle, capital Phi, and the SMEFT. So you need a technique to tell you if you propose some super symmetric theory or some, something with some extra particles. When you go to low energy zone, when you integrate out that heavy particle, what SMEFT Lagrangian you get? So namely, what are those Wilson coefficients corresponding to this UV theory? Okay, so that's the basic task of this part. Okay, so then in this part, the task is to do this what we call matching calculation. That is, suppose you propose a UV theory with some top partner or something, then you have your SMEFT that you observed with Wilson coefficient bounded at some level, or right? Okay, so how do you match the two? Okay, then naively you should just do, traditionally you do this thing, right? You find a set of amplitudes, you calculate what's the UV prediction for those amplitudes, and you calculate the same set of amplitudes again with your EFT with this unknown Wilson coefficient. Then you require that they are the same. So that the two series are equivalent at the low energy, right? Then you solve for those boson coefficients. That's the procedure to do this matching calculation. But clearly, if you are going to do it this way, you need two ingredients beforehand. You need to know all the effective operators here to start with so that you can calculate this set of amplitude with the EFT. You also need to know what set of amplitude should I look at such that I can fully determine all the boson coefficients. So if you have some secret redundancy in this operator set, you will typically get in trouble in practice. Right? It looks like you cannot determine all of them. Okay. So that's the pitfall people have literally, got into in the past in this matching procedure. Okay.
Oh, but as a guiding principle, you take, for instance, you can do the following. Take, let's say, for an example, as an example, some kind of grand unified model. Okay. And in this grand unified model, you have very heavy vector bosons, X, Y, and so on. You don't know exactly the mass, but they're very heavy. Now you integrate, take one. I mean, there are a few consistent grand unified models. Take one model, integrate out all heavy particles, because in this particular model, all interaction vertices, right? You can legitimately integrate out all your heavy particles and then descend down to our energies, let's say TeV energies, okay?
Yes.
This will give a set of extra of these dimension 6 operators, which appears in this particular model.
Exactly.
You take another grand unification, do the same, and then you can compare. I bet there will be almost 100% overlap, because that's, if both unifications are consistent with experiment, it's very hard to invent something new.
Yep. Yeah. So basically what you are saying is we need a more systematic way of achieving this matching calculation, right? And there, in your example, there are, right, this systematic way of doing that. That's exactly where I'm going here, right? So ideally, you want a way that your UV Lagrangian, then you can directly derive this EFT at the low energies without, going through this, case by case calculation, right? So, okay, so then how do you systematically achieve this step, right? And there are many ways, and for different cases, there are also different, options. But one option to do that is to use this so-called functional method to achieve that. So the basic idea, again, is very simple. Then instead of requiring each individual amplitude to be the same from the UV calculation and the EFT calculation, you now match the so-called 1pi generating functional of those amplitude. You match this 1pi effective action. So once they are matched, they're the same, then it's automatically guaranteed all the amplitude will agree. So then this is just making this matching abstract to this effective action level, right? So then you systematically wrap all this requirement into this functional form, okay? But then the good aspect of that is you can actually at the abstract level solve this equation and get an explicit expression of this EFT Lagrangian in terms of the UV Lagrangian. Okay, this expression look like this up to the one loop level of calculation. So if you require the UV and the EFT 1pi effective actions to be the same, you can solve it at the abstract level and just get this explicit plug-in expressions. Okay, so at tree level, you just find, so this capital phi is your heavy particle that you're integrating on. And then at tree level, you just plug in the solution to the equation of motion and you get the EFT Lagrangian. And at one loop level, you do a few more steps. It's like you get the second functional derivative of the action and plug in the equation of motion and evaluate this functional determinant. But that's a systematic way of doing the calculation. So it applies to any matching calculation, basically. Okay, so this is a powerful systematic way. The only technique you need to know of using this expression is how to evaluate this super trace or functional trace. Okay, so that's a technical aspect I will not discuss in detail in this talk, but you can go to this references to learn how to do this this functional trace evaluation. Well, in principle, let me emphasize that it's just a textbook level object, right? It's just a functional trace. So you can evaluate it, use any technique you like such as Feynman diagram evaluation is fine. Okay, but then we prefer using this purely algebraic way of evaluating that, which is totally equivalent to the Feynman diagram thing. It's just then this is called so-called covariant derivative expansion technique, and because it found many applications, and we realized that people are not that familiar with this covariant derivative expansion technique, so we automated it into this stream package. So super trace evaluation automated for matching. So that's a stream. But then later on, we realized that some other group actually is also working on the same thing. They call it super tracer. So if we had known other people are working on it, we wouldn't write this paper. And, but then we only learned that by a week before we posted this paper. So then there's some clash. And let me say that we were not seriously just writing some complicated code to a fully automated matching procedure, but this group of people, super tracer, is actually doing that. So they are writing a much more complicated and more powerful code for the automation of this super trace evaluation. Okay, so that's this one. And let me mention also there are some advanced techniques in functional matching. So if you use functional method, it also gives you some additional things. For example, sometimes we want the matching result to the all order in the field. For example, if you think your UV theory is such a theory that after you integrate out the heavy particle, you actually get this EFT. Then if you expand in the usual dimension 6, dimension 8, dimension 10 SMEFT sense, then you get this series of boson coefficient and effective operators. But secretly, they're just from this single operator with this h mod square in the denominator. So is that possible that you do your matching calculation and directly get this red expression instead of get this truncated one at each order without knowing the full story being this one, right? So this is the matching result to all orders in the field. Okay. Then it turns out that this is possible, and it's actually famous, and in the textbook, it's called Komen-Wimber potential. We do that all the time, right? Think about this toy example. You have some heavy field phi scalar, then you integrate it out, you just evaluate this functional trace log of this operator, right? With this interaction encoded in U of phi. Now, this is a functional trace to evaluate, but if you think this U of phi is constant in space-time, namely the commutator between the partial derivative and U is 0, then you go ahead and do the evaluation. That gives you this black part, this first part. That's the famous Komen-Wimber potential. So you can just pursue along this line, just turn on the next commutator. This is a Baker-Campbell-Hausdorff procedure, right? And then you just keep to next order, this is a partial square piece, and truncate it there, you will get the next order. So this is our tiny bit generalization of Komen-Wimber potential, and then you get this result. So this is truncated in the power of derivative, but it's to all the powers of the field U of phi here. So it's not truncated at any mass dimension 6 or 8 or anything. So this is especially useful if you are matching onto something like a nonlinear sigma model where you do need all powers of the fields, and it's naturally a derivative power counting in the EFT. Okay, so other advanced technique is like anomaly matching. So all I'm talking about so far is about matching the Lagrangian. So you have some UV Lagrangian and you integrate some heavy particle, then at low energies you have an effective Lagrangian. But we know sometimes if you integrate all fermions, then you could break the anomaly cancellation structure of the UV theory, and there's some effect of the anomaly remnants in the low energy EFT. So you should be able to see those, such as the Weiss-Zumino effective action, and how does it come out of this matching calculation, right? And also recently there was also some confusion about anomalies in EFTs with spontaneous symmetry breaking. So people claim that in SMEFT there's some additional anomaly cancellation conditions, but turns out to be false. And then so this also helps you to clarify things like that. So this is an ongoing project, and should we should publish 2 papers soon in December, maybe. Yeah, hopefully. Okay, so that's this part about the EFTs. Okay.
For the super trace technique, is formula similar integrating all the fermions?
Yes. Yes.
I recall there was some difficulty with integrating all the fermions. People say, can you say a few words?
Yeah, you can go to this papers and check how to do it for fermions, gauge bosons. They all work.
Let me solve it later in 2019.
Actually, in 16, we even in 14, we already explained how to do it for different spins, but it's kind of buried. It's a long paper. Yeah. We this paper in 1412 it's called How to Use SMEFT, and then it's a 100-page paper, and then it's buried there. Yeah. Okay. Okay, good. Let me move on to the last part of my talk. Is some deep challenges for EFTs. So is SMEFT enough? So let me first tell you that there's something called heft, and we need that. Okay, so what is heft? Heft is, so this picture is like this. You have standard model, and then SMEFT has more interactions a lot, and heft has more. So it's bigger than SMEFT. Okay. Then this traditionally was called electroweak Carroll-Lagrangian, because the idea was like, there are W and Z bosons, but before you discover the Higgs, people thought, okay, you need some way to break electroweak symmetry such that the gauge bosons got mass. And then one way of doing that is doing this similar thing to the Carroll-Lagrangian, QCD Carroll-Lagrangian, right? You just do it that way. It's a nonlinear realization of the electroweak symmetry breaking. Okay, so that's what heft is. So nowadays people call it electroweak Carroll-Lagrangian with a physical Higgs. So that's heft. Just an alternative names. Okay. Then, so what is this thing? So we know there is a physical Higgs boson now discovered at the LHC, and the 3 gold stones accountable for the masses of W and Z bosons. Okay, so in SMEFT, you group them into this SU2 doublet. But in heft, you just say they're separate fields. They don't have to form an SU2 doublet. That's it. Okay, so you treat them as separate fields. And you use this nonlinear parameterization, this Goldstone matrix, to parameterize it. So if you write down the Lagrangian, for SMEFT, people call linear realization, you just write down things like capital H is the linear representation of the electroweak group SU2. But if you write it in terms of little h and U, the matrix U is a nonlinear representation, or nonlinear realization, more accurately, of the electroweak symmetry. So that's a nonlinear thing. But this is just a very formal terms. So in practice, we just care, what are the operators sitting here? Can you give me an example that's sitting in the blue shaded region, where it's just beyond SMEFT, the operator list, right? And it's in heft, right? If you're looking for that, it's here. The kinetic term of the physical Higgs boson. It's even in standard model, right? But if you just look at this operator alone without any goldstones, this is an operator allowed in the heft parameterization, obviously. But if you write it back into the doublet form, capital H, you can always do that, right? Then you will find this operator. You could write things back to the SU2 doublet formalism. So that's why it's confusing. People originally thought they're just a rewriting of each other. They're just field redefinitions of each other, but it's not. Okay, because this one you see, you have this H mod square in the denominator. It's non-analytic at capital H equals 0. But when you enumerate the SMEFT operator basis, when you enumerate all the possible interactions here, you didn't allow for this dimension 4 operator. So implicit assumption there is analyticity. You're saying my Lagrangian has to be a polynomial of all those field components and their derivatives. So I don't allow for this kind of non-analytic interactions. So that's the only place where halved is bigger than SMEFT. You basically turned on allow for this non-analytic kind of operators. Okay.
Sorry, if I do integration by part for this operator, what will happen?
You can do that, and that's the kinetic term. So in that sense, the integration by part doesn't apply, right?
No, if I do that, it come back to a normal operator that I have. That's my normal kinetic term, right?
For which side, this side or that side?
The pink side.
The pink side.
Yeah.
You do integration by part. How do you get rid of this 1 over h mod squared thing?
Integration by part, you get h squared times box h squared. H squared or h squared.
I'm sorry, derivative on 1 over something gives you 1 over that thing squared.
Oh, I need to do the denominator.
Yeah. So so non-analyticity is there. It's preserved. Okay. Yes. Yeah. Thanks for the question, though. Yeah.
It's a good question. So this H scale can also be coming from just the del H scale, right? So just the capital H square.
This operator?
Not that operator, but just the operator.
Yeah. Yeah, but yeah, the kinetic term of the standard model. Yeah, it contains this, but it's not this one alone. So that's why, right, in SMEFT, you basically group them together, right? They have to come together. If you talk about the Higgs, physical Higgs kinetic term alone, that's not an analytic operator in SMEFT.
You can change the kind of term of this H and the pi's.
Yeah. So that's the degree of freedom you turn on, you have. Yes, exactly. Yeah. Other questions?
But sorry, just to be clear, your claim is that the only such operators that wouldn't be in SMEFT are non-analytic.
Yes.
And if you try to write them in SMEFT paper.
Yes. Yeah, because they SMEFT and have share the same set of particle content. They're all just a standard model fields, and they preserve the same set of symmetries, the standard model symmetries. So like I explained at the very beginning of defining EFTs, you specify field content and symmetries that determines your EFT. But I lied slightly there. I didn't tell you there's also an implicit analytic assumption when you enumerate the interactions. And that turns out to be the essential difference between SMEFT and half.
I guess I'm a little confused. Does SMEFT not have this additional SU2 doublet symmetry, or is that secretly encoded in
SMEFT preserves SU2 symmetry.
Yeah, but half doesn't.
Yes.
But is that secretly encoded in the half here?
Yes. This is so-called CCWZ formalism.
Okay.
Yes. So in the nonlinear realization, it looks like you're just explicitly preserving the subgroup, but you're actually equivalent of enumerating all the operations, interactions preserving the bigger group. So you have a bigger group G spontaneously broke down to subgroup H. Then for each broken generator, you write down a Goldstone field due to Goldstone theorem. And then you write down the Goldstone matrix like this. And then you use the Goldstone matrix as a building blocks of your phenomenological Lagrangian due to Weinberg, right? And then what's so-called Carol Lagrangian, right? Then, right, it's a tricky subject to try to preserve the big group G. But it turns out that if you follow CCWZ prescription to find the linearized so-called Cartan-Moria variable, then you can just you linearize the theory, and then you can enumerate operators. And then you just need to preserve the H, the subgroup, but it actually preserves the bigger group. So in halved, it looks like you're just preserving E and M, but you're actually preserving SU2 cross U1. Yeah.
So, so is there any also is there any difference in the interaction between Higgs and other matters? Like, is there any difference between SMEFT and the like, this is about Higgs sector, right?
Mm-hmm.
But do you also have any difference in the other sectors, like interaction between H, like Weinberg operation, for instance?
For you mean fermions and gauge bosons?
like not just the parent, like interaction between parent and H, like operators that involves not only H but also like fermions.
Yeah, it turns on. Yeah, it's sort of separate the right the so.
You also write down some different operators.
Yeah, but you can imagine in practice, it's just like your right. If you roughly say capital H is just the V, the valve, little v plus little h, you're just sort of reorganizing that expansion in SMEFT, right? So ultimately, things can be rewritten into each other.
Okay.
The only caveat is this non-analyticity. Yeah, that's what I'm emphasizing.
Yeah, I understand the difference, but just want to make sure. Why do I want to expand the H around 0? Shouldn't I expand around the valve?
That's right. That's what I will get to that. That's right. Exactly. So that's why people claim half is the most general EFT for beyond for standard model. Like if you build standard model as a EFT, you should go to half. That's the most general version. SMEFT further assumes analyticity at the origin of capital H, which is unnecessary. Exactly. Okay, let me move on. Okay, since I'm running out of time. Okay, so we know now halved just has this non-analyticity at capital H equals 0. But what does that mean practically in terms of particle physics, right? The phenomenology. So one argument that's emphasized by the Chan, Luti, and Falkowski and Rattazzi in 2019 is that if you have a non-analyticity at the origin of capital H, then you will find there's unitarity violation at 4 pi, the scale 4 pi times electroweak scale V. So that means the new physics have to kick in before this scale happens. Okay, if you have this non-analyticity. So the way they demonstrated this argument is this way. So they consider this pi goes down scattering to n Higgs amplitude, pi to Hn. Then they show that this for large enough n, it grows as this n factorial divided by this v to the n. So then if you sum over this cross section and record that it doesn't violate unitarity, right? You see that the scale is bounded by 4 pi v. So that's their approach. So it's just this amplitude growth is the problem. Okay. Then you could find this amplitude growth by say, if you turn on this non-analytic, right? The square root of h mod square. So that's non-analyticity at h equals 0, right? You just expand it into the v plus h part and the Goldstone part, and you keep it up to pi square piece, and you find this structure. So if you have a potential like this, then you see the amplitude will grow like that. So that's one way of seeing this, right? But that's basis specific, right? Actually, this behavior is very easy to understand from a abstract level. This is something called just a complex analysis. This is called Cauchy-Hartmann theorem. So this is saying if you have any function, a single variable complex function, right? You view, for example, the potential as a function of the physical Higgs H on the complex plane of H. Then Cauchy-Hartmann theorem tells you this. If you find a non-analyticity of this function at a certain point, that means your Taylor expansion around the origin cannot converge beyond this convergence disk. Of course, if you think about the Taylor series, it's a series. If it doesn't converge, that means the tail must be growing fast enough. So it tells you the Taylor expansion tail, the derivatives, namely, how fast it has to grow in order to not be converging at this point. So if the convergence radius is given by R, then the derivative, higher order derivative for large enough n must grow like this. That's just a very simple fact of complex analysis called the Cauchy-Hartmann theorem. But you see in this example, if you have VH, the potential in your EFT Lagrangian, and you know it's non-analytic at some place.
But
R.
in the expansion, you have in front of the n derivative 1 over n factorial until Taylor series, right?
Yeah, you can move this to the left-hand side.
This is an artifact. In physics, it may come as if all these particles are identical, and then when you couple it, I mean, when you single out the raising or
the symmetry factor is,
There is-
yeah.
there is combinatorics, but let's say all these particles are different.
Okay.
Then you don't have this n factorial and the amplitude.
Okay. Okay. So it's a matter of defining this thing, right? So amplitude is defined as nth derivative of the potential.
Why that all you have is just a neutral pi method. It's identical and all particles produced are identical.
Mhm.
Then of course you have this n factorial because of the combinatorics. But
Yes.
then, as you know, because of their identity, the phase space have to be divided by n factorial, and the amplitude, the cross section is not dependent on n factorial at all. So this is a deceptive thing what you wrote.
Yeah. Unfortunately,
Because take the function 1 divided by 1 minus x. It is not convergent beyond mod x equal to unity.
Mm.
But it's a totally normal function. It's it's has a very mild pole, one pole singularity. It produces normal amplitude in the domain where you don't hit the pole. They don't grow, nothing terrible happens.
oh, we can talk about that later if you are.
There's nothing to.
Yeah,
nothing to
I think we work out the combinatoric factors very carefully, and this argument does hold in the example you just said. Okay. Okay. Okay.
He's not arguing that there's not the n factorial in the amplitude. He's just arguing that when you calculate a physical quantity like a cross section, that you also divide by n factorial.
That's right.
And your cross section stays fine.
But cross section is a square of this amplitude. So you have one n factorial here, then squared. Then in the phase space, you have another 1 over n factorial. So, but then still you have.
Sorry. 1 n factorial for identical particles. There's another n factorial for conservation of energy momentum. Because the phase space volume of a scattering process have to conserve that. So it's not the momentum.
Oh, I'm talking about the phase space.
Yeah. So there's identical particle under n factorial.
That's taken care of here by the amplitude.
No, but he's saying you have to divide by n factorial when you're calculating a cross section.
I have to.
But that's after square this amplitude.
Yeah, but then there's another,
n
Right, right.
Conservation.
so they cancel.
So yeah, you think about like a populate space, right, of two particles. I can populate the momentum of two particles arbitrarily. However, conservation of energy momentum shrink that into a sphere. So there's another reduction of volume compared to two arbitrary.
Let's talk about this afterwards then. Okay, I want to, if you think, if you think they cancel, that would be interesting. Okay. Yeah, but I don't think they cancel. Okay.
But there's a big volume reduction when you have to make the sum of all the free particles momentum to be contained within certain value.
No, real factorials do appear if vacuum is unstable. Like for instance, Dyson argument, right? But it appears through loops. Because loops acquire imaginary part, which is leakage in the vacuum, leakage in the states in the vacuum. It's exponentially small effect, and weakly coupled theory has nothing to do with this.
Okay, so I just want to be clear here. I'm not talking about the Higgs explosion in the slides, okay? So if you have any sort of opinion about if Higgs explosion is a real problem in experiment or something, I'm not talking about that, okay? And the only thing I'm saying is when you have non-analyticity at the origin of capital H, you will find this behavior of the amplitude growth, that's all. They can be linked. Whether that's a real experimental problem or not, when you go to the cross-section level, that's a different question in principle. The question is, how do you identify this singularity at h equals 0 that can be linked with this unitarity violation? Whether you call it unitarity violation is also another thing, right? Yeah. Right. Right. We never really have unitarity violation. It's all an artifact of your approximation of your tree level perturbation of your right. We know that, right? Your Hamiltonian's Hermitian unitarity is guaranteed. Okay.
I'm gonna have to run in a minute, so I just wanted to ask a quick question. Sorry to keep piling on. So normally when I think about effective field theory, I don't try to write anything non-analytic in the fields.
That's right.
Right? Because such things would arise if I accidentally integrated out somebody massless, roughly speaking. And I don't normally want to do that from a Bosonian point of view. So like, why are we talking so much about this case?
Yes, that's the next slide, basically.
Okay,
yes. So usually when you write down a Lagrangian, you want to have a well-defined Feynman rule, vertices, right?
Yeah.
So the derivatives must be well-defined. That's your Feynman rule. So by assumption, the Lagrangian is analytic at where you expand. If your physical vacuum is 0, phi force, for example, phi force theory, you don't have a 0, you don't have a valve. Then, right, that's the way you read off the Feynman rules, the vertices, that by taking this derivatives with respect to the potential. That's your Feynman vertices, right? So it has to be analytic at that point. So same thing for standard model. It has to be analytic for physical little h equals 0. But it doesn't have to be analytic at capital H equals 0. That's the mismatch between SMEFT and HEFT. Okay, so you sort of assume that it has to be analytic in SMEFT. That's the thing people miss when they restrict themselves to SMEFT.
You're saying the form of the effective field theory would change completely if I dial the Higgs mass parameter so that there's no electric.
Not Higgs parameter. Not Higgs mass.
Location.
Yeah.
So where I expand around.
So let's walk through the slides, okay? So it's like this. You have some UV theory. You integrate all the heavy particles, you get an EFT. Then suppose your EFT looks like this. So this capital M square is your UV particle mass, and they interact with Higgs, so it gives you this kind of effective Lagrangian. So what is happening is what I talked about is in the case that this M square is 0. So you see, if M square is 0, you can attempt to expand into SMEFT, but if M square is 0, that expansion doesn't exist. That's where the singularity sits right here at the origin of capital H. The HEFT is defined. You're perturbing around this physical vacuum. You have well-defined Feynman vertices in terms of little h. But you go here, you run into trouble. So if you want to write it in terms of capital H, you just don't have any expansion. So this is theoretical level, you have HEFT because SMEFT expansion doesn't exist.
Of course, if the heavy scale you want to integrate out is light, you cannot integrate it out.
Yep.
What's the point here?
Yeah, so that's the next one. So you can imagine another case, which is M is not exactly 0, but it's small compared to this second term. So it doesn't, the SMEFT expansion doesn't converge.
You cannot integrate at the scale out if it is small compared to the interaction term. What are you integrating
I agree with
out? I mean, this scale is important at the scale of where energies your work at. So you cannot integrate it out.
Yes.
It's obvious to everyone. Why so much ado about that?
Yes. So this is exactly, your point is valid. Exactly. You're talking about, in these cases, there's new physics coming in very close to the electroweak scale, right? So that's what we call non-decoupling BSM physics here. Non-decoupling in the sense it's tied to the electroweak scale. So in this case, you should not integrate out the UV particle in the first place because the EFT would not be a good approximation anyway, as emphasized here, right? But if some people still do it, right? If you do it, then you should use HEFT instead, because SMEFT is not even a convergent series, because the good approximation or not is all about truncation in principle. If you don't truncate, you sum the series to all order, right? It's still okay. But then if the series is not convergent, you cannot even sum. So this way, this HEFT is like an analytical continuation of this sum of SMEFT, right? So the convergence radius of SMEFT is here in the brown part, but it doesn't converge at the physical vacuum because the singularity is sitting too close But then you formally resum them and use this halved form, and that's the analytical continuation of the theory, if you wanted to integrate out. Okay, so that's the meaning of halved. So halved is linked to non-decoupling physics. Okay, so that's, well, now back to this question. Is there any scenario that practically at the LHC that it could make sense still when you have this non-decoupling physics, you still integrate out and use a low energy EFT, right? So you can think of this. So what does it mean for when the singularity is sitting close? That means the second term, when you take H equals a half V squared valve, that's bigger than the first term. But it doesn't mean M squared has to be very small because kappa could be bigger. It only tells you that if this is a UV particle, capital phi, its full mass is given by this. It only tells you it gets mass mostly from the Higgs interaction. This second piece is bigger than the first piece, is here. So this kind of particle, we name it as Lorentz. And that's the type of particle that could be relevant for integrate out and get halved at the LHC. So I agree, this is a very tiny band of window when this halved is technically, practically irrelevant, is relevant for the phenomenology. Yeah, but that's some cases you could look at and search for. Okay, then bounded by something like a 4 pi square, but that's some space. That's where, right? When you talk about the practical particle, that gives you from 250 GeV to something like 5 TeV. That's where LHC is looking at. Come on, right? Right. So if you think that factor of 10, 20 is not important, that's all LHC is doing, right? You don't have access to beyond, 10 TeV at the LHC anyway. Right? Why do you build that tunnel? Why do you dig that tunnel? Okay. All right. So then, okay, I see I'm running over time, but I guess I'm still finishing the talk. Okay. So this is all about when halved is relevant. Okay, it's just a linear realization, non-linear realization. The difference is just the singularity. Okay, then the story is not that simple because sometimes you could have fake singularities, such as this. You thought you have some non-analyticity at H equals 0. But by a field redefinition, you can rewrite it into something like looks like a purely healthy in terms of capital H1, the new field. So there are singularities, looks apparent singularities, but they're not actually singularities. So you need some more, field redefinition robust way of telling when you do have a singularity, what we call physical singularity, that points you to nonlinear realization, instead of this fake kind of singularity that can be removed by field redefinition. So this is what I call deep challenge for EFTs in general, because you have field redefinition ambiguity here that gives you a lot of subtleties there. So this was recognized by Alonso, Jenkins, Manor back to 2016, where they say one can always attempt to convert from halved to SMEFT using something. But if you do this, right, the Lagrangian in terms of the SMEFT phi, which is capital H, their phi is my capital H, then need not be analytic in phi, named at the origin of this phi. Okay, but they say if there's an O4 fixed point, then you can find a field redefinition that make it analytic. So they give you a criteria. If there's an O4 fixed point on the manifold of the field space, then that's a criteria that you can use field redefinition to remove the non-analyticity and get back to linear realization.
Sorry.
Yeah.
Is this different from just compute a curvature of this Taylor space and let's see if there's a singularity or not? Like this criteria?
This is even before that. That's this slide. Okay. So the overall fixed point is this. So the idea is like you view this Higgs sector, which is 4 real scalars, physical Higgs and 3 bosons. Right, this is a 4-dimensional manifold of this 4 coordinate. So each point on the manifold is you take some value for little h and boson. So you are only accounting for there are fields, but you're only taking them as a number at each point, right? So you're only taking constant modes for those fields in this picture. Okay, that's why it doesn't accommodate derivative field redefinitions. Okay, But in this picture, you can consider the O4 transformation. This O4 is the SU2L cross SU2R custodial symmetry. So they consider custodial symmetric version of the SMEFT. Okay. Then you enter this custodial transformation, the manifold transforms, right? It rotates. It's a symmetry, so it's rotation. But then you see there's difference between this and that. On this manifold, every point is moving under this O4 rotation. So there's no point that stay fixed under the O4 custodial transformation. But on the right-hand side, you have a point that stays there under this rotation. So they say if you have an O4 fixed point, then they use this common Weiss-Zumino linearization lemma, this is CWZ before the CCWZ, and to argue that you can find a linear realization by a proper field redefinition. So that's their basic principle. Again, I will not give you the proof or dive into details of this argument. But what they apparently miss is that the criteria they say is like, if there is a fixed point, of course, it doesn't move under the O4 rotation. So the metric must be 0 along the goldstone directions, right? So that's their criteria. But this is miss something is like this scenario where that point is there, the metric is 0, but it's a kink point. It's a cusp point of the manifold. So it's not part of the analytic manifold. So it's just in the linearization lemma, there's a prerequisite, which is we talk about the analytic manifold in the first place. But if there's a kink point on the manifold, it's not a part of the analytic manifold. So technically, in this case, this point, although it seems like satisfying Alonso-Jenkins Manaher criteria, but technically it shouldn't be viewed as part of the manifold. So it doesn't exist. So that's our tiny correction to their argument here. You also need to check this point is not a non-analytical point. Namely, you calculate the curvatures and those things and check that it's finite. Okay, so that's our contribution to this. So then this tells you a geometric picture to explain when the non-analyticity at h equals 0 is physical. Then we know it gives you this unitarity violation. So you can also make a geometrized version of that argument and show that why unitarity violation has to show up by writing the amplitude into curvature quantities, covariant quantities. So this semicolon is a covariant derivative of the potential and this of the Riemann tensor with further covariant derivatives here. So this is the Mandelstam variable. So you can systematically write all the amplitude into this geometrical quantities and then argue that unitarity violation is independent of the coordinate change, namely field redefinition. Then this is a geometric picture for that. But as you see, this whole picture is based on identifying this two derivative term form factor as a metric on the manifold. So when you do a field redefinition without derivatives, this tensor, this factor will transform as a two tensor. So that's a metric. So it clearly doesn't accommodate the field redefinitions with derivatives. So this is only for field redefinition without derivatives. So how to generalize that to include also derivative is a recent work we did earlier this year. Since I'm running out of time, I will just tell you briefly that you can just write down the full 4-point function. For example, you see it's a contact piece plus 3 channels of this decomposition. And you can just identify this part as a Christopher symbol. Then using this generating functional language, you can recognize that sum as a partial derivative or a functional derivative from the 3-point function that gives you the contact piece. And then 3 channels of a Christopher symbol with the 3-point function. So this is nothing but a covariant derivative on the 3-point function. So this picture generalizes. So n plus 1 point amplitude is given by a covariant derivative in this sense on the endpoint. So this is a tensor-like recursion relation. So that means it transforms properly as a tensor under field redefinition, arbitrary field redefinition now. This is including derivatives. So this is a new development we made recently and generalized Alonso-Jenkins and Manaher to accommodate derivatives as well. Okay, so that summarizes my talk. So in this talk, I walked you through several different important aspects of the effective field series, including like how to define the effective field series, namely constructing EFT operator basis, then how to use them as a theory to interpret experimental measurements, especially emphasize the validity issue, and we propose use perturbative unitarity as a hint for EFT validity, and similar to the validity of usual loop perturbation, and also how a functional method can help you to do the matching, and also I didn't mention running calculations. And finally, I tell you that there's some deep challenges for EFT formalism, that is field redefinition. So I told you how to use a geometric picture to address those questions. Okay, thanks for your attention. Happy to address any additional questions.
Any more questions?
So you were arguing that SMEFT implicitly assumes analyticity at H equals 0, but half doesn't, so half should contain like operators that SMEFT doesn't. Can you do the opposite logic and say that half is implicitly assuming analyticity at like little h equals 0, which is capital H equals B, so it must contain some operators that SMEFT doesn't?
You can do that, but because little h is physical.
Right, yeah, I figured that heft is still the more.
Yeah, so for all the physical cases we're interested in, you have to assume analyticity at little h equals 0 anyway. Otherwise, what are we doing at the LHC, right? How did we discover Higgs, right?
But like technically in terms of Venn diagrams, like it's not like
technically you could, yeah, you could, yeah. In general, most generality you could consider, yeah, of course, yes. Thank you.
Example, it's confused with